Imagine you've drawn dots on a piece of paper, and you want to maximize how many pairs of those dots end up sitting exactly 1 unit apart. How fast can that count grow as n gets large? This is the famous unit distance problem, posed by Paul Erdős back in 1946, and despite being elementary to state, it has resisted serious progress for nearly 80 years. The best upper bound, due to Spencer, Semerady, and Trotter, says you can't do better than roughly n to the 4/3. The best lower bound, due to Erdős himself, was n times a tiny factor involving the logarithm of n. Erdős conjectured his lower bound was essentially the truth. He was wrong. The reason this matters beyond pure mathematical curiosity is that it sits at the heart of combinatorial geometry. Erdős's original construction used a clever grid in the plane. Take an n by n lattice of integer points and count how often the distance between two lattice points equals 1. By number theory, integers can be written as sums of two squares in many ways when they have lots of prime factors, and this gives you the small logarithmic boost over n. For decades, nobody could push past this barrier. Then very recently, a team at OpenAI, with Li Jie Chen guiding an internal model and Mark Selke and Mehtab Sawin verifying the work, finally cracked it. They proved you can achieve n to the power 1 plus some positive delta, disproving Erdős's conjecture. But their delta was left unspecified, and a follow-up by human mathematicians made it explicit at roughly 6 times 10 to the negative 38th, which is astronomically small. This paper by Will Sawin brings that exponent down to earth, proving you can get n to the 1.014, only about a factor of 24 away from the conjectured upper bound exponent. So how does the construction work? The unifying idea is to think bigger than 2 dimensions. Instead of placing your points directly in the plane, you build a high-dimensional lattice and then project it down to the plane. If your lattice has many short vectors that all project to vectors of length exactly 1, then taking a ball-shaped chunk of the lattice and projecting gives you a planar point set with many unit distances. Think of it like casting shadows. A complicated 3-dimensional sculpture can cast a shadow with many coincidences that the shadow alone couldn't easily achieve. The richer the higher dimensional structure, the more unit distances appear in the shadow. The natural source of these high-dimensional lattices is algebraic number theory. You take a number field, which is a finite extension of the rational numbers, and its ring of integers naturally embeds as a lattice in a real vector space, whose dimension equals the degree of the field. Specifically, you want what's called a CM field, which is a totally imaginary quadratic extension of a totally real field. Inside this setup, the projection of a lattice vector to one chosen plane has a squared length that lives in the smaller, totally real subfield. Since that subfield has fewer elements available at small size, by pigeonhole, many different lattice vectors must share the same squared projection length. Divide through and you get many vectors whose projections have the same length, which after rescaling gives you many unit length projections. Erdős's original argument is exactly this construction with the simplest possible choice, where the big field is the Gaussian integers and the smaller field is just the rationals. To beat Erdős, you want number fields where the smaller field has many primes that split in the bigger field, and where the class number, which measures how badly unique factorization fails, is well controlled. These two demands pull in opposite directions, and the way to satisfy both is to use a construction called the Golod-Shafarevich tower. The idea is to start with a base field and repeatedly take its maximal unramified extension of 2 power degree, building an infinite tower of fields whose discriminants grow only exponentially in the degree, which is as slow as possible. The Golod-Shafarevich criterion is a clever inequality involving the number of generators and relations of a certain Galois group. If relations are scarce enough compared to generators, the group must be infinite, meaning the tower never terminates. The trick adopted from work of Hajir, Mayre, and Ramakrishna is to quotient this Galois group by a power of the Frobenius elements at chosen primes, which forces those primes to have small inertia degree, meaning they split nicely in the resulting fields. That ensures the fields in the tower not only exist, but actually have the many small split primes the construction needs. Sawin's contribution is to take this entire pipeline and sharpen every step. He works with arbitrary ideals rather than just the ring of integers, which makes the pigeonhole argument cleaner. He uses the relative class number, the ratio between the class numbers of the bigger and smaller fields, instead of the absolute class number, which gives a tighter bound. He uses Louboutin's analytic bound on the relative class number rather than the cruder Minkowski bound. He drops the restrictive assumption that the relevant primes must split over the rationals, which had cost the OpenAI argument enormously because primes splitting in a field generated by many square roots are typically exponentially large. And he uses the probabilistic method on the ratio of unit distance pairs to total points, rather than on the raw count, because the average lattice ball contains far fewer points than the worst case. When you plug in concrete choices, the construction works out as follows. Sawin picks the set of small primes T to be the first 13 odd primes and another set called S sub Q, consisting of 22 primes, including the small ramified ones and a handful of larger inert ones. He carefully assigns multiplicities K of P to each prime, choosing them by an approximation formula that balances the gain from many split primes against the cost of large discriminant. Each K of P starts large for small primes, like 50 for the prime 2, and tapers down to 6 or 7 for the larger primes. After running these numbers through the master inequality, the exponent delta comes out to about 0.014114. So sets exist with n points and at least n to the 1.014 unit distances, divided by some absolute constant. The paper also addresses some natural follow-up questions. By a clever argument about subgroups of two groups, Sawin can produce these fields at many different degrees, which means the construction works not just for a sparse sequence of n, but for a positive density set of values of n up to any threshold. And he gives an analysis of the theoretical limits of this strategy. Even with ideal assumptions, the basic combinatorial number-theoretic framework can prove at most an exponent of about 1.243, which is comfortably below the upper bound of 4/3, or about 1.333. So this entire family of arguments will not close the gap on its own. What are the limitations? The construction is highly non-constructive in the sense that you need to invoke deep theorems guaranteeing infinitely many number fields with prescribed local behavior. You don't get an explicit recipe for the dots. The exponent, while explicit, is still far below the conjectured truth, and the analysis shows the framework cannot reach the upper bound. Improvements would require either better analytic control of relative class numbers, which runs into the notorious problem of potential Siegel zeros, or entirely new lattice constructions. There's also a tantalizing question about whether the artificial intelligence pipeline that produced the original breakthrough can be pushed further, but that's separate from the mathematics. Now let's walk through some questions you might have after hearing all of this. Why does projecting a high-dimensional lattice into the plane give you more unit distances than just working in the plane directly? The key is that the high-dimensional lattice has more algebraic structure than any planar lattice. Its vectors live in a number field, and the lengths of their projections are constrained by elements of a smaller field, which forces many coincidences in projected length. A planar lattice doesn't have this hidden algebraic scaffolding, so it can only exploit the much weaker coincidences coming from sums of two squares. What role does the Golod-Shafarevich criterion actually play in the proof? It's the engine that guarantees you have an infinite supply of number fields with controlled discriminant. Without it, you could pick one nice field but couldn't push the degree arbitrarily high while keeping the root discriminant bounded. The criterion converts a counting inequality about generators and relations of a Galois group into the conclusion that a tower of field extensions never terminates, which is exactly what you need to send the degree to infinity in a controlled way. Why does using ideals instead of the full ring of integers help? When you're forced to use the ring of integers, you have to express your collection of elements as multiples of some single principal element, which loses information whenever the relevant ideal isn't principal. Working with arbitrary fractional ideals lets you directly use whatever ideal naturally arises from the pigeonhole argument, avoiding the loss from approximating it by a principal ideal. It's a small technical move, but it tightens the inequality at a crucial step. Now, what does any of this have to do with large-scale recommendation systems? On its surface, nothing, but there's a worthwhile structural lesson. Many production retrieval systems rely on approximate nearest neighbor search in high-dimensional embedding spaces, and the geometry of how many items can sit close to a query point governs both the recall and the index size. The unit distance problem is essentially asking how degenerate this geometry can get, and the constructions here show that lattice-based embeddings drawn from algebraic structures admit far more coincidences than generic random embeddings would. If you're designing a learned retrieval system where you want to control the number of items at exactly some target similarity, knowing that algebraically structured lattices can pack in many such coincidences suggests you should either inject randomness to avoid pathological collisions or exploit such structure deliberately for things like hashing and quantization. More concretely, the probabilistic averaging trick Sawin uses in his lemma 2, where translating a ball randomly through the lattice gives a sharp ratio bound, is the same flavor of argument used to analyze random projection retrieval and locality-sensitive hashing. When you build a candidate generator that buckets users or items by random hyperplane signatures, the same ratio between average and worst-case bucket sizes governs your serving cost. The deeper takeaway from this paper for systems builders is that the gap between what generic random constructions achieve and what cleverly structured constructions can achieve may be much larger than intuition suggests, and that closing that gap can come from importing tools from completely different fields, in this case, algebraic number theory and class field theory, into seemingly unrelated combinatorial problems.